Hi, I'm Taylor, a staff technical program manager on the Calibration, Localization, and Mapping team. Just like humans, Zoox vehicles need to understand where they are in the world before they can safely and successfully navigate to their desired destination. In order to do this, they require three things. 1. Knowing the exact positioning of their sensors. 2. A map of the world. And 3. To understand their location on the map. Multiple departments at Zoox work together on this vital part of self-driving, and we do it all in-house. The software developed by our CLAMS, which stands for Calibration, Localization, and Mapping simultaneously, and ZRN, or Zoox Road Network teams, allows our vehicles to accurately, precisely, and consistently understand where they are and how they are moving through the world. This mission-critical data is used by all the other systems in our autonomy stack. Before it can drive, the vehicle must understand where its sensors are located with respect to each other, as well as the vehicle body. These positions are calculated through a process called calibration. Calibration is critical because it allows the vehicle to see a clear and consistent view of the world. Without a good calibration, the vehicle could perceive the world as cross-eyed. Similar to the way your brain uses the information from your two eyes to deliver a crisp, singular view of the world, our system uses overlapping sensor data to precisely calculate where each sensor is mounted on the vehicle. This precise understanding of sensor locations gives our vehicles the ability to perceive obstacles at great distances. Many approaches in robotics use very specific, predetermined patterns to calibrate a robot's sensors. Zoox vehicles, however, use the natural environment to calibrate their sensors without the need for any special infrastructure. This is important when driving in a city, as you can't set up special calibration targets everywhere the vehicles will drive. Here, you can see how we automatically identify color edges in our camera data and align them to depth edges in our LiDAR data. This extremely reliable and super precise sensor calibration is the hidden backbone of solid mapping, localization, and perception systems. So, what comes next? Maps. The first step in expanding our testing to a new city is the CLAMS and ZRN teams building maps for our L3 test fleet to drive. Instead of relying on dedicated mapping vehicles, we drive our retrofitted Toyota Highlanders, the very same ones we use for autonomous testing, around the area that we want to map and capture data about their location and environment. Because our sensor architecture is the same on our L3 test vehicles and our purpose-built L5 vehicles, we can use any type of vehicle in the fleet to update our maps. After this raw data has been collected, CLAMS builds a precise, high-resolution 3D map of the area with automated tooling that aligns LiDAR point clouds and estimates the vehicle's trajectory. We also use our perception pipeline to semantically understand what objects should be part of the map and what shouldn't, like people and cars. The resulting map is then delivered to the ZRN team for annotation. Here you can see our 3D map, colored by our perception system's automated semantic segmentation pipeline. The ZRN team then works to build the road network on top of the 3D map. The ZRN includes features like lane markings, stop signs, traffic lights, speed limits, keep clear zones, bike lanes, and other important road information. These two maps are then layered together and automatically downloaded onto the vehicles, along with the newest software build. These maps supplement the vehicle's real-time perception inputs, giving the vehicle very helpful hints about what to expect, especially beyond the immediate field of view. Having this map data allows our vehicles to do a better job of safely navigating from A to B. So, now that the vehicle has the map of its environment, it's time to work out where on that map it is. This process is known as localizing, and is done by matching real-time sensor data to the map. In the same way that we use our eyes and inner ears to sense motion and orientation, the vehicle is equipped with a variety of sensors that contribute to its understanding of how the vehicle is moving through the world, including wheel speeds, steering angles, IMU sensors, which include gyroscopes and accelerometers, and GPS. Our localization software fuses many types of input data to let our vehicles know where they are, which direction they're moving, and at what speed, with a great deal of precision. It is this combination of calibration, localization, and mapping that provides the strong foundation that our vehicles need to be able to safely and accurately navigate through the world. Of course, our streets are ever-changing, so our vehicles need to be able to recognize new conditions and make adjustments in real time. For example, our vehicles can detect a previously unmapped construction zone and change lanes to avoid a closed lane. As they drive, our vehicles use their perception system to automatically compare features like the lane lines against the map. When a vehicle detects changes in the map, or degradation of its sensor calibration, it can send reports back to our CLAMS and ZRN teams. These teams ensure that the vehicle is recalibrated or the map is updated. In situations where one vehicle finds something like a road closure, and we need an even more rapid response, we can flag that part of the map for teleguidance support, or even block off that changed road in our map to immediately prevent all other vehicles in the fleet from driving there until our map is updated. So there you have it, an overview of how Zoox vehicles are able to understand their location in the world in order to autonomously navigate from A to B. I hope you enjoyed it. Be sure to subscribe to our YouTube for more videos about our approach to autonomous technology.